This one you want to think about only during class. Get the components. Get the components. You were able to get them. Yeah, he's the bearing on the this, oh actually, that's a good one. You don't know, you can make it like X and Y, make it easier. Is 0 because he's not moving thousands. Make it 2,000 for half of it, just pull it in. Now it's going to look like we're having class where we have to do that XY system. Oh, you're so kind of close. Make components. And then you're going to add on the overall result is this vector, which would be 0. See it? And then so it's a lot like Kramer, with like a system of equations. Let's go to the right idea. Okay, good.
Space. Okay. Guys, remember today's goal is not necessarily to go over all these word problems. However, I want you all to peek at really quickly, and this is the one I slowed down on most of yours just to look at, number 91, because number 86 was kind of similar to most, or 85, 86, what was that one? 85. Yeah, that was kind of similar to an example what we did. Number 96, we basically peeked at, and it was using the triangle SOHCAHTOA of the one that we did. It was just like something else on an incline or at a different incline. But numbers 91 and 101 are the ones I was most interested in. 101 had to do with bearing, and we never actually finished that example, and that's totally fine. We're going to look at bearing on Monday for sure. Like that one's going to be Monday. But number 91, sorry, some people are gone. I should probably be doing this in your notes. Number 91 is the one I was most interested in as to what you tried to do. Because the picture looked different than the crane problem, and yet the idea was so similar. And I saw, basically, those of you guys that had a really good attempt on it, most of you, I'm pretty sure you used Slater, because you're using notation that I never showed you, with big old capital T's. Or like big old magnitudes with linear combinations. I'm like, why are you using linear combinations? Like, who likes the I's and J's? That's weird. And there were multiple ones of you around the room. I'm not saying that it was bad to use Slater. Like, I understand it. I'm just worried that you're going to look at that problem and be like, I could never do that on my own. And it's like, actually, you could have. And how you could have would have been using, and I showed those of you that got stuck and were like obviously stuck in the sense that you're like, okay, I drew the picture, I kind of tried, and I slowed down and I showed you what was going on. But I'm afraid that even those of you that had a solution, you have not much of a clue. Or if you do, you think that it's way more complicated, or at least you need to be using all this physics terminology that you really didn't. Because for instance, in class, I said, you could use magnitude of u, cosine angle, magnitude of u, sine angle, but I also said you could just use an x, like a system of equations unknown, with cosine of your angle. Now this is number 91. I'm not solving the whole thing, I'm just kind of helping out. We have what seems to be kind of like a different situation from the cranes, because you have like these two coming together and holding this load. This load is, I think, 2,000 pounds, something like that. And we have, help me out guys, is it 50 and 30? Is it that way or is it the other way? Oh, perfect. Okay, cool. So basically what we have are these two cables, and I know it's technically one, but there's tension in these two separate lines, or these two separate parts of the cable, or the whatever is holding it. I don't think it's rope. You have these two separate vectors, and so you could call this guy U, you could call this guy V, and they're combining to actually uphold this load, and so they're combining to be this 0 and negative 2,000. Why 0? Well, because this guy's right component, horizontal component, this guy's left component are canceling each other out to be able to have this guy be straight down. He's not at an angle, there is no horizontal displacement in this vector, it's just straight down. So this guy technically has an overall component of 0, and then down, not up, would be negative 2,000. So he's the resultant of these two working together on the load. So I have x cosine of 50, sure. X sine of 50, sure. I don't need to be using capital T's for tensions, or A's and C's and B's, and I don't even know. I don't need to be using magnitudes of u's or linear combinations. I can just be literally following the crane problem. And even in the crane problem, we had these first quadrant angles that weren't necessarily in the first quadrant. And so I took a yellow pen and I talked about it, and I did a YouTube video on it, and I told you to go check it out. But I know the picture looked different. You didn't maybe realize it was the exact same situation. So that's why I'm drawing the comparison now, so you can think about it and rework it and see if you can actually make sense of it yourself, maybe in a simpler way. We need to think about how this 50 degrees is technically in the fourth quadrant, not the first. So 50 degrees has a positive cosine and a positive sine, a positive x and a positive y. But guys, what does this actual vector have? Who needs to stay positive and who needs to go negative? Sorry.
The sine side.
Good. The sine needs to go negative because it's going down. The cosine gets to stay positive. But if we were to come over here to the 30-degree one, who needs to go negative?
Cosine.
Cosine and sine because it's going to the left and down. So if you want to use this first quadrant angles, there's no problem in that. You don't necessarily have to make new angles. You just have to make sure that your sines are indicative of the actual horizontal vertical components of this vector. But they're reference angles. That's okay. No stress. You can use them. You just have to kind of keep your wits about you and be thinking of the picture along the way. At this point, I'm pausing because if you don't know what to do next, go look at the crane problem because now it looks exactly the same. Not the picture, but the math. And follow exactly the math that we did there, just with different numbers. All right, guys, so section 6.4, our goal today was to get to work. So you guys are on this page. People that missed yesterday, I am so sorry, and I can't totally perfectly reenact the craziness that was yesterday. However, we had some sick people, we had some next to friends people, and we had some just very talkative always people. But I can reenact part of this. Long story short, I want you to imagine that the stool is the box at point P. I want you to imagine I have a rope over my shoulder. If it wasn't a minimum bid, I would actually go get my rope and I would show you, but that's okay. Imagine it. You guys are creative. A rope over my shoulder tied to the stool, and I start walking and dragging my stool. If I start dragging my stool, work is being done because I am putting in a force and I am covering a distance. The problem is, I cannot just, not that I would even know it, true, we have to have like an instrument to measure the amount of force I'm putting in, but okay, let's just pretend we knew the amount, I knew the force that I always put in whenever I put my back into it. I don't know. Literally, putting your back into it, ever heard that? That's where it comes from. Especially when you're dragging, you put your back into it, you're trying to put extra force to get it done. Anyway, I have that rope over my shoulder, I'm dragging. The force that I'm putting in is going up at a diagonal line, like you can see in the picture, capital F. The problem is, that is not the capital F that I get to just strictly take the number and plug it in my formula, because work is defined to be the force in line with the motion of the object times the distance it covers. So technically, this formula, the force in line with the motion is what is over here, and then the distance that's covered from P to Q, for instance, which we could technically say is the length PQ. The other way of saying that would be the magnitude of PQ. But the distance is how far it moves. I need to multiply distance times force, but the force needs to be in line up. So am I putting in force? The answer is yes. Can I just multiply that force times the distance that I travel? No. I need to figure out how my force that I'm putting in at an angle is projecting onto the line of motion. Now, the tricky thing is that this whole thing could be at a slant on a hill or something else, and all of a sudden, I wouldn't be able to solve it quite as nicely as I'm going to be able to, because my projected wouldn't be a right triangle with a normal horizontal axis, so it'd be a little bit harder, but we don't have to worry about it, because I said yesterday, on the test, you're only going to see work that is being done on a horizontal surface or a horizontal line. So anyway, all that to say, we don't need to really stress about all that projection stuff on the page before that helped me figure out projection on slants or angles. I get to just think about, wait a minute, okay, so I can use the snazzy word projection. I can even have a formula that says projection. But to be honest, I don't even really need to think about projection, because isn't this a right triangle? I don't have to think about this crazy projection formula on the page before. There's only an arrow because technically we were drawing a comparison yesterday being like, hey, the projection that you just saw, where's my smartboard marker? Nope, nope, yes. We were looking at the page before being like, it's used in work. But the nice thing is we don't really need that, because all we need to do is to solve our right triangle. So instead of that crazy projection formula, I'm erasing it and I'm saying, once again, like number 96, if you actually figured that out from our notes from our example, which you should have. If you had the triangle for the thing on the incline, you can do the same thing here. You can take your force that's being put in at an angle for an object. You can take an angle at which it's being done, and all you need to do is solve for the actual force in line with the object that we're going to be plugging into our formula. Now, I know it's awkward because that's a force and that's a force. It's just which force. This is the force that is being done for me pulling it over my shoulder. We could put it S for shoulder. I don't know. That's not always the case, though, as to what's being done. You could just be like pulling it at an angle. But anyway, there's the force that's being done at an angle, and then there's the actual force that I need for my formula. And it's really as easy as, wait a minute, adjacent, hypotenuse, all I need to use is cosine. All I need to use is cosine. So at the end of the day, the force that I'm going to go ahead and be plugging into my work formula is the force being done at the angle with cosine of the angle. If I were you, remember, I'm saying there are some crazy physics problems out there that we could be having to do, but we're not. So even though projection is the idea, even though this whole, like, the force is being done here, but what's actually happening to the stool, because the stool's not literally traveling up my shoulder, it's moving this direction. Better not be traveling up my shoulder. I need to find the other projected force. The idea is projection, but to be honest, all I need to think about is a right triangle to get that number to plug in times distance. So down here. This one is actually a simpler, harder problem in that this one shows a P to a Q, and this one's being done at a slant. Let's see, 1, 3 is the first quadrant, -3, 5. It's being done at like a up to the left slant. But to be honest, the idea, if you were to do it this way, and if they were to give you all this nice, super neat information, what we could do is say, okay, wait a minute, all we need to do for work is multiply force, which in this one I could technically make a component form, times distance. Well, if they give it to me like this, I can do my P to Q, terminal minus initial. I could do my little, hey, we've been practicing this because you guys were supposed to have this homework done a couple days ago. Terminal minus initial, terminal minus initial. I could have two dot products, or I should say two vectors that to multiply, all I have to do is, do a single dot product. So this is a complicated one. This one, the motion isn't being done in a horizontal line. This one, I don't really know what the object is or exactly how it's moving or why or how someone is doing this force at a weird angle to drag it. But because of the points given to me, component form being easy to find, components, well, linear combinations being given to me, my guys that put I's and J's, why are you writing it like this when you can do this? Anyway, the harder problem becomes easy, but the dealio is as soon as they start actually talking about objects that are being dragged, etc., we would have to find the component form, and that's what some of you guys were really struggling in those word problems. So even though this is a valid type of work, dot product of two different vectors, the distance vector and the force vector, it's good, it's just not very realistic in how information would be given to you. Which is why on the next page, the last example, for section 6.4, with an object and like an actual word problem, it's not at a slant like this one. It's not at a slant like this one. This one is along the ground, and we're pretending it's level ground. So we have a tractor that's pulling at an angle, that's pulling a log, sure, why not? That's pulling a log, and that log is dragging a certain distance. Do you guys kind of get the picture? There's a log on the ground. Okay, I know it's not on the ground, but whatever. There's a log on the ground. Pretend the log is a box, because why not? And the tractor has a cable attached. It's dragging it But even though the tractor is dragging at an angle, that's being projected as this force that is pulling the log along the ground. Now, the nice thing is, guys, check it. They gave me 35 degrees. Cool. Got it. Projection always comes down at a right angle, so I can say, hey, it's a right triangle. And how hard is the tractor pulling, or I should say with what tension is the tractor pulling? That's what that is, right? Tension in the cable connecting the tractor and the log. Yep, it's 15,691. Since it's being pulled on a horizontal line or a horizontal surface, I can say work is as easy as this force that I need to find, the one that's projected down in line with the motion, times distance. And how far is the log dragged? We have this thing called newtons that some of you maybe you're seeing for the first time. It's a thing in physics. It's a unit of work. But coming back, how do I solve? I just get to plug into my nifty formula as long as I know my picture of force at an angle with cosine of the angle. Guys, look how easy it is. Plug it in a calculator. Is the concept hard? Yes. Projection. Is the idea hard? Oh, is the solving hard? No. You're solving a right triangle and saying, oh, that's my force times distance. Dun, 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 dun. Wait, what are we solving for? Work? What are Newton meters? That's weird. Anybody know Newton meters? Nobody knows? Joules. The unit measure of work. Newton meters are the same thing as joules. Although I'm pretty sure the book will just say Newton meters because it's like, they're Precalc, they don't know. Anyway, you guys, homework 6.4, due on Monday. Due on Monday. I don't think I tried to give you any work ones that were done at angles, or if I did, they weren't like a real life problem. They were just like the components of the page before, just do a dot product. Projection, maybe I gave you one just to play with the dot product, but not on the test. Bye guys. Monday we'll talk about bearings, what's going on there, and grade homework. See you guys later. My Slater people, thank you for thinking through Slater. Just make sure you're not making it harder than it needs to be. They do sometimes.